So, hello everybody. Thank you for being here. In this presentation that I called Hacking and DIY on a Parrot drone, I will present you the fruit of my research. So, first of all, who am I? My name is Eliot Badinga. I'm a 21 years old student at the school CPE in Lyon. I'm also a CTF player under the name HoHoHo. And I'm currently running on an internship in Switzerland as a pen tester. So a very important thing I want to say is that I'm definitely not an expert, but more passionate, so I can make mistakes. And please, if you see one, tell me at the end of this presentation. So my talk will be divided into several parts. So first of all, I'm gonna present you the project. So to what were the objectives and the constraints. Then I will talk about my role in this project, the problem I had to face off. I will talk a little about the methodology that I use in this case. Then I will talk focusing about a more technical aspect, so the reverse engineering. So two parts, one part for the hardware reverse and one part for the software reverse. Then I will quickly talk about some DIY that we made on the drone, and I will conclude with my feedback. So where is the problem? Yes, so the project presentation. In my school, every year, the second year student must participate in a group project. So basically, this project consists by making a robot whose functionality is to follow a line pretend on the ground. But this year, they give us a choice to choose our subject. So with my group, we choose these options. And I'm not going to enumerate all the ideas that we had, but we started from an electromagnetic musical instrument to end with a plane. But the plane was a little bit hard to build, so we chose to build a drone instead. So there were three constraints for this project. The first one was the time, only 4 months, so it's pretty short. The second one was the budget. It was around €0. So yes. And the last one is that we need to use an STM32 in our project. So with a €0 budget, we can't did everything we wanted to do. So luckily, the robotic department of our school gave us a Nair drone. So this is the drone. But the motherboard of this drone was broken. So the objective was to replace the broken motherboard of the drone by the STM32. We also had a Raspberry Pi to broadcast video stream by making a Wi-Fi hotspot. And my role in this project was to understand the component that we wanted to keep. So it includes only the motorboard of the drone. So I talk about motorboard and not just a motor, because as you can see, there is an electronic circuit that controls the motor speed. And the problem is that in the Parrot company, everything is proprietary, so it includes the hardware, the software, and the communication protocol. And that's the reason why I'm talking about hacking and reverse engineering. So for my methodology, it's quite simple. The first thing I did was to look on internet to find some piece of information that I can use in order to have a starting point. Then I did 2 phases of reverse engineering. So one for reverse hardware, and I continue with software reversing. Then I made my first conclusions. I did a couple of tests in order to verify my first results, and then I made my final conclusion. So I use some hardware tools in order to perform my research. So the first one is this cheap logic probe that I bought on Amazon. I use an Arduino to make some basic tests and a multimeter to measure current and voltage. I also use, of course, a voltage generator. I use some software too, so Ghidra and IDA for the software reverse engineering. Logic Plus to analyze the communication between the component, and Binwalk to understand some proprietary file format. So I begin with the hardware reversing. So as you can see, and as I said, it's not just only a motor. You have three main components on it. So the first one is a transistor. So there are three of them, two here and one here. The goal of the transistor is to generate a PWM signal in order to control the motor speed. Then you have a microcontroller that receive the command and control the transistors. And then you have, of course, the motor, so it's a brushless motor. You have also 5 pins on the motor board. So with the multimeter and continuity test, we can assume that the two first one are for power supply. So one for the motor power supplies and one for the microcontroller power supplies. You can assume that one pin is for the ground too, but there are 2 pins that remains. So on internet, they said that the motorboard communicate by UARTs, but not the classical UARTs. In fact, it's one-wire UART, so the TX and RX data are transmitted in the same line. And there is another pin that remains. So on internet, they said that this pin is for receiving an ERQ signal, but in fact, this is more simple than that. This pin is used to activate the motor, because I will explain this later. So I was able to get a functional drone in order to perform dynamic hardware reverse engineering. So I just put a logic probe between the motherboard and the motorboard, and I analyze the data that were transmitted. So this is a summary. We can notice some bytes. So E0, 50, 71. These bytes will be useful in our software reverse engineering. So for the software reverse engineering, I went on the Parrot official website and I downloaded a PLF file. So it's a file to perform a firmware update on the drone. So PLF file may be for Parrot something firmware, but we don't really care. So this file was on a proprietary format. So I use Binwalk in order to understand what were in it. So as you can see, we can split the file into 2 parts. So there is 2 Z image. I split the file with the command DG, and I analyze the 2 parts separately. So the first one is a basic busy box. There is nothing interesting on it, but on the other one, once you have uncompressed the data, as you can see here, there is a strange file with a path at the beginning of the file, then followed by 12 null bytes, and then you have the real content of the file. You can see the magic signature of an ELF file. So I wrote a simple script in Python in order to recover the file system, and it gave me that. So you can see we have a lot of file and a lot of interesting files. Since I was only interested by the motor, I used the command grep in order to find some string references to motor. And I quickly found an interesting file called program.elf. So one important thing I want to say is I'm not really good in software reverse engineering, but that's okay because I have two techniques that help me a lot. So the first one is to start from the call to the libc start main functions. As you know, the first argument of this call is the address of the main functions, so I could start here. And the second one is to search for string references in the binary. And of course, I renamed the functions and the variable in the pseudocode in order to come to a better understanding. So my first technique was to start from the call to the libc start main functions. So this is the main functions, but the problem was the fact that the main function call a lot of a whole bunch of functions, and these functions call also a lot of functions. So it was pretty hard to understand. So I followed my second techniques. So to search for string references, so I started by searching the string motor, and I quickly find another interesting string, the term BLC. So maybe for a brushless controller, as I said, the motor are a kind of motor that we call brushless. So with these strings, it's allowed me to quickly identify the functions related to the motor control. So I'm not going to explain all the functions I had to reverse, but I'm going to present you the most important one. So with this one, for example, it's a function that deal with the initialization process between the motherboard and the motorboard. So you can notice that this is the same bytes as we saw earlier. So E0, E1, and 40. So the behavior of these functions can be summarized by this diagram. So the first thing the function do is to send the command E0 in order to get the motor state. Then it gets the motor checksum by sending the command 91. And it responds with a checksum of 120 bytes. Then the motherboard send, there is a process between this step and this step. I will explain in the next slide. Then the motherboard send the command A1 to start the motor. And if everything is okay, the motor is started, the motherboard send the command A0. Then the motherboard assign an ID to the motorboard. So there are 3 motors, so 3 ID. And then the motherboard sends the speed command to the motorboard. So as you can see, there are 2 kinds of commands. So unicast command, the command must be sent to only one motor. And there are some broadcast command, multicast command, sorry. And they must to be sent to every motor. So as I told you, there is a complex step at here. So this is the process. So the program load a file called blc.x and decode it. So it's a basic Intel X format. It's very often used to store firmware in IoT. Then the program copies the process, copies the firmware, the decoded firmware into the memory. Then it calculates the checksum of this firmware and asks the checksum of the firmware that is running on the motorboard by sending the command 91. Then it compares the 2 checksum, and if they are not identical, it sends the command 71 to the motorboard in order to rewrite the motorboard firmware. So this is the process to rewrite the motorboard firmware with the command 71. So the firmware is splitted in two chunks of 64 bytes, so 60 in total, and sent piece by piece. Another interesting function is this one. So this one explains how the motherboard controls the motor in speed. So as you can see, the speed is encoded in 9 bits. Sorry. And the speed of each motor is then concatenated to form a command of 5 bytes. So this table explains that. So this table summarizes my results. As I told you, the command E0, 71, etc. So now we were able to do some tests, some basic testing. So in order to do that, I use my Arduino as a motherboard. And I put my logic probe between the Arduino and the motorboard in order to get the motorboard results. So as you can see, it's work. When I send the command E0, the system, the motorboard responds me with 50. So everything is okay, but there is a strange thing. When I send the command 91, the system responds me with a very strange checksum, so C0, C0, C0. I think that the motorboard firmware, was corrupt. So I test the same script on another motorboard, and it seems to work because the LED turned green when I send the command A1, so in order to start the motor. So in order to repair my broken motorboard, I made this setup. So the firmware of the motorboard is too big to be stored on the Arduino, so I had to buy an external EEPROM memory of 32 kilobytes. Then I wrote piece by piece the motorboard firmware in the EEPROM memory, and then I calculated the checksum of the firmware, and I compare it with the file, with the firmware file, and it was the same, so everything is good. But, and I made another script in order to rewrite, so the script read the memory of the EEPROM and send the firmware to the motorboard. And it's worked because when I send the command 91, the motorboard responds in the response of the motorboard, there is not only C0, so I was able to reflash the firmware, but when I send the command A1, the LED stopped blinking and the motor crashed, so I didn't know why. So I use a functional drone and a functional motherboard to rewrite the firmware of the broken motorboard, and it's work because I hadn't the time to understand why my techniques didn't work. Then we did some DIY on the drone. So the first thing we did was to cut all the connection with the motherboard, and we solder our lab cable, and we had heat shrink tubbing over the world in order to secure the thing. And we had two breadboards on the side of the drone in order to facilitate the debugging and the connections in case of error. So another thing is that, as I told you before, we need to use STM32 as a motherboard, but the STM32 sends a UART command with a voltage of 3.3 volts. So we need to make this basic setup. So it's a logic level shifting in the objective to increase the voltage of the height logic level to 5 volts because the motorboard only understands UART in 5 volts. Another thing that we needed to do was to implement a demultiplexer, because as I told you, there is two kinds of command, unicast and multicast command. And in order to send a command only on one motor, we need to make this basic electronic circuit. So I use this component, and this is the final result. So as you can see, there is the STM32, the demultiplexer, and the logic level shifter. We also had a converter 12 volt to 5 volt in order to power all the components. And this is the result. So here I test the result with an Arduino. So as you can see, the LED turned green, and the drone started flying. Yes, like this. But there were some stabilization problems, but that's okay. We did the same test with the STM32 and the logic level shifter, and it's work. You can see the motor don't fly, but it's work. So conclusion and next step, we needed to add the sensor and to configure the PID. So it's basically it's an algorithm for stabilization and controlling command. So we need to find three constants for this algorithm. And the last step was to connect the Raspberry Pi with the drone. But unfortunately, we didn't have the time to do that. So we stop here. But a professor of my school has taken over my research and continue it with other students. So the project is not finished yet. Then, nevertheless, it remained a very instructive experience in many areas, particularly in teamworks. So I loved conducted this research, and it was for me first time. So that's the reason why I'm presenting, I'm sharing it with you, sorry. So that's all. Thank you for your attention.